In this tutorial, we're going to be looking at sets. We're going to start by defining sets. We take a look at set notations, the types of sets, set operations, and lastly, we look at Venn diagram. To start with, how do we define sets? We simply define sets as any clearly defined collection of things, objects, or numbers. Sets is any clearly defined collection of things, objects, or numbers. For example, a collection of materials in a mathematical set, collection of books in a library, or simply a collection of students in the class. Also, a set can be a collection of different things. It can be of different type. We can have a set that consists of numbers and also letters, even animals like goats. This is also a set. Conventionally, each member of a set is called an element. For example, looking at this set, each member of the set, we have 1, 2, 3, 4, 3, A, B, C, and goat. Each member is called an element. And also, we use capital letters in representing sets. For example, you can say this is set A in capital letter equals to 1, 2, 3, and so on. And we use small letters in demarcating the elements of the set. Also, note that the order in which a set is written does not matter. For example, if you have a set A to be equals to 1, 2, 3, and set B to be equals to 3, 1, 2. These two sets are quite equal. They are equal. We are going to be looking at equality of sets in the next tutorial. Later in this tutorial, we are going to be looking at equality of sets. So we are going to talk about how these two sets they are equal. Now let's talk about some symbolic representations. We have noticed that a member of a set is referred to as an element. If an element X, small letter x, belong to a set X, that is capital letter X, we say that X is an element of big X. So to represent this, we can simply say X is an element of X. This is small letter E. It's something like 3 in reverse order. So we say X, small letter X, is an element of X, the capital X. And if X is not an element of X, we simply negate this. We are saying, for example, we have Y is not an element of X. So we have looked at two symbols, this and this. The symbol E is read as is an element of. So if you say we say A, small letter A, is an element of A, and symbol E with a slash is read as is not an element of. Just like if you have equal to and not equal to be slash equal to, so we can say this is an element of, and this is not an element of. Here's a quick example. We have a question which says if Y is a set of all even numbers and A equals to 6 and B equals to 7. So A is 6, and if you are listing even numbers, we know 6 is an even number, so we can say that A is an element of Y. And B, which equals to 7. 7 is an odd number, it's not part of even number, so we can say that B is not an element of Y. So this is a quick example just to show the difference between element and not element of. To continue, we have looked at sets and what an element of a set is. Now let's look at set representation. How do we represent sets? If you want to write a particular set of numbers or a collection of a defined numbers, objects, or things, how do we represent this? There are 3 ways we are going to be looking at in this tutorial. The first one is by listing the elements of the set. So this can go like this. We have A to be equal to 1, 2, 3, 4, 5. So this one representation, we write a set A and we list the elements. For example, we have marked B, A, B, C, D. So we list out the elements of this set. So that's the first method of representing set. The second we are going to be looking at is by describing the elements of the set. And this is what we looked at in the previous example. We can say that set A, is a set of all prime numbers less than 10. So here, instead of listing out all prime numbers that are less than 10, we simply use a word to describe this, like set A equals to set of all prime numbers less than 10. You might have another example by saying set B is a set of all even numbers between 10 and 20. So this is still representation by describing the element of the set, and we can write out the element of this set by saying set B equals to 12, 14, 16, 18. So this is actually set B, but instead of writing it out like this, we use a word to describe it. So that is the second method of representing set, by describing the elements of the set. And the third one we are going to be looking at is the use of range. So how do we go about this? We can say that a particular set A equals to x such that 1 less than x less than 10. So what does this mean? It means x is a number and these are the range in which x falls to, 1 less than x less than 10. If we were to write out the element of this set, we can say the element is equal to 2, 3, 4, 5, 6, 7, 8, 9. And we are going to have other conditions to support this. X is going to be defined whether x is integer, a whole number, a fraction, or any other number format. So we can also define another set B to be equals to all prime numbers this is all prime numbers such that 1 less than equal to x less than equal to 10. So this simply means we are defining all prime numbers that falls between 1 and 10, including 1 and 10. So we can list out the element of this set. It can be in any format. We can also say C equals to x such that 2 less than equal to x less than equal to 20. And we're going to have a definition such as like where x is an integer. So here we have seen that the range in which x falls to includes 2 less than or equal to x less than or equal to 20, and we know that x is an integer from this definition. So to write out the element of x, we can start listing from 2, 3, 4, and so on till we reach 20. So these are the ways in which we can represent a set. The first one is by listing the element of the set. The second one is by describing the element of the set using words, and the third one is by using ranges. Now let's move to types of sets. The first type we are going to be looking at is finite and infinite sets. In talking about finite and infinite sets, we define finite set as sets in which the elements are finite. That is, all the elements can be listed. On the other hand, infinite sets are sets in which the element continues to infinity. For example, if you have a set A which is defined as all integers, so if you are to be numbering or listing this set, you are going to have 1, 2, 3, 4 till infinity. So this particular set are referred to as infinite. That is, you can't finish numbering them. It's going to continue till infinity. And for finite sets, for example, if you have a set B that equals to even numbers less than 10, so we can see that we can list all the elements of the set. For example, we can have another set which is the days of the week. So we have 7 days in a week. We can list all the elements. So these are finite sets. And infinite sets are sets in which the number of elements proceeds to infinity. If you continue to number them or list them, we can't finish the listing. Let's look at an example here. The question says, show whether each of the following sets is finite or infinite. The first one, all months in a year. This is a finite set. Since we have how many months in a year? We have 12 months. And we can start listing them from January up to December. The second one we have here is all numbers greater than 10. This is an infinite set. So if you are to be listing all numbers that are greater than 10, we are going to start from 11 upward, and we can't finish listing up to reach 10 billion, 20 billion, continues to infinity like that. So the third one is positive numbers less than 10. This might look very long, but it's still a finite set. We can list right from 0 to 99. So that is a finite set. So the third one is finite. And the fourth one, D, say all odd numbers. This is an infinite set. Infinite set. So we can't list all odd numbers. It's going to proceed to infinity. So this is an example of infinite set. So that is just an example to compare infinite and finite sets. Now let's continue. Another category we are going to be looking at is the subset and superset. We have looked at sets, like we can define a set A to be equals to elements and set B to be equal to its own elements too. So in a situation whereby we have two sets, for example A and B over here, if set B contains some or all the elements of set A, then we say set B is a subset of A. For example, let's change this to a real element. For example, we have set A to be equal to 1, 2, 3, 4, 5, 6, and 7. And we have set B to include 2, 3, 7, and 6. So here we can see that set A contains the number 1 to 7, and set B contains 2, 3, 7, and 6. And all elements of set B are also in set A. So we can say that set B is a subset of set A. It's something like set B is being derived from set A. Like set A gives birth to set B, something like that. So how do we represent subset? We represent subset by using a letter. It looks like C, but it's not C. But something like this. So with the present condition, we can say that set B is a subset of set A. We simply write, let me write this again, B is a subset of A. This looks like C, but it's not C actually, just like a curve. Yes, set B is a subset of set A. And if this is the case, set A here we refer to as superset. Hope that is clear enough. Set B is a subset of set A, while set A is a superset of set B. A set that is being derived is referred to as a subset, while the master set is the superset. For example, if you have set X to be equals to days of the week, and we have set Y to be equals to Monday and Friday, so we can say that set Y is a subset of set X, and set Z is a superset of set Y. So how do we represent superset? We simply represent superset by just making another symbol that looks just like the opposite of subset, something like this. So we can say set X is a superset, so it comes like this. Yes, set X is the superset of set Y. Remember, the master set is the superset, while the derived set is the subset. This is subset, and this is superset. Looking at another example under subset and superset, if you have a set M, let's say the set equals to 1, 3, 5, 7, 9, 11. These are odd numbers, and we have set N to be equals to 5, 9, 11, and set O here to be equals to 1, 3, and 8. So if you take a look at the contents of set M, which are the elements of set M, and look at the element of set N, we can see that all elements of set N are also in set M. So therefore, set N is a subset of set M. Also means that set M is a superset of set N. But looking at set O, we have an outlier which is 8. 8 is not in set M. So we can say that 8 is not an element of set M. Therefore, it renders set O not to be a subset of set M. Even though we have 1 and 3 to be in set M, but because of 8 which is not in set M, we cannot call this a subset of set M. So therefore, set O is not a subset of set M. So I simply represent this by crossing out subset. So we can say that set O is not a subset of set M, and also set M is not a superset of set O. So that is simply how we can represent subset and supersets. In the beginning of this tutorial, I made mention of two sets that are equal, and this section of this tutorial is dedicated to talking about equal sets, which is referred to as equality of sets. Two sets A and B are said to be equal if the elements are the same. Note that the elements are the same. As we note earlier, the order of arrangement of these elements does not matter. The first one can be in orderly arranged, and the second one might be scattered. In as much as they have the same elements, they are equal sets. We use the symbol equals to represent equal sets, and not equal to this to represent not equal set. So this is read as is equal to, and this is read as is not equal to. So if you have set A which is equal to set B, this is read as A is equal to B, and if set X is not equal to set Y, we read this as X is not equal to set Y. Let's look at an example. If you have a set A which equals to X, Y, and Z, and you have set B which equals to A, B, and C, and from here we can see that even though they have 3 elements, 1, 2, 3, also set B 1, 2, 3, but the elements are not the same. We have X, Y, and Z here, but here we have A, B, and C. We can see that set A is not equal to set B. Another example here, we have a set X which equals 5, 6, 7, 8, and 9, and set Y which equals 9, 5, 7, 6, and 8. So these two sets, they both have 5 elements, but we can see that from set X, this is arranged in other element of 5, 6, 7, 8, and 9, but set Y is arranged as 9, 5, 7, 6, and 8. Checking this very way, we can see that they both have the same elements, even though they are not arranged in the same manner. So we can see that set X is equal to set Y. So that is simply about equality of sets. Two sets are said to be equal if their elements are exactly the same. And note again that the order of arrangement does not matter. To continue, we are going to look at universal sets. In talking about universal sets refers to like a set that encompasses a lot of other subsets. It's like a general set in which all other sets in that particular consideration are derived from it. The set which contains all possible elements under consideration is referred to as universal sets. For example, if you are talking about a particular sample now, we can have a universal set to be equal to all months in the year. So from this set, we can now form all other sets from it. We can say another set A equals to months that start with letter J. We can say another set B, which is months that ends with letter R, and so on. So we represent universal sets by the letter. It's something like U, but it's not totally U, but you can also use U to replace this. So this is represented as universal sets. To look at another example, let's look at some sets here. So we can define universal sets U to be equals to 1, 2, 3, 4, 5, and set A which equals to 1, 3, 5, and set B which equals to 2 and 4. So we can see that this universal set contains all the elements that we are looking at in this particular consideration. It contains all the elements of A and all the elements of B. So this is how they are referred to as universal sets. We are going to be seeing more examples on this in this tutorial. And then, what is unit sets and empty sets? As the name implies, unit sets are sets that contain or consist of only one element. For example, you can have a set A which equals to 1, another set B which equals to only Monday. We can see that all these sets contain only one element. So these are referred to as unit set. It's as simple as that. How about empty sets? Empty sets, they are null sets. They can also be called not sets. They are sets that contain no elements. Sets that contain no elements. For example, you can have set A. So there's no element there. And this also represents how we can write empty sets down. Empty sets can be represented as just two curly braces without any element, or we use a letter. So these two symbols are used to represent empty sets. Let's say, for example, if you say set B equals to all human beings with tail. So set B asks you to list all the names of human beings with tails. You can see that there's no any element on this set. There's no human being that has tail. So you can say that set B is an empty set. Set B is an empty set. So that is simply difference between unit sets and an empty set. Okay, we have been looking at different types of sets. Now we're going to consider complementary sets, and this one is quite complicated, and we're going to do justice to that. Now we have looked at universal sets and some other elements of sets. So it's this we are going to join together to form the complementary sets. Now let's get started. Given that A is a subset of the universal set U, then all the elements in the universal set that are not in set A are referred to as complementary sets. Let me take that again. If you have A as a subset of the universal set U, then all the elements in the universal set that are not in set A are referred to as complements of set A. Let's take, for example, we have set U, which is a universal set, which is defined as 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we have set A with the following elements 2, 7, 8, and 10. So this is universal set and this is set A. We define complementary sets as the elements, or to put it in a better way, the set of all the elements in the universal set that are not in set A. Now let's bring out all we have in universal set that are not in set A. So, okay, before we proceed, we can represent complementary sets or the complement of a set by saying A prime, or we simply put AC, which represents A complement. So this is A complement, another one A complement. So now let's find A complement. So I prefer the one with prime. So we have A complement to be equal to, here we have 2, 7, 8 and 10 in set A, but in universal set we have 1. It's not in set A, so it's part of complement of A. We have 2 in set A, and in universal set that is not there. We have 3, we have 4, 5, 6, 7. 7 is in set A, so we didn't include it. 8 is in set A, so we are not to include it. 9 is not in set A, and these are the sets that form the complement of set A. So that is how we can define the complementary set. Another example, if you have universal sets which contain all alphabets in English, and we have set A which consists of all vowel letters. So if you are to find a complement, it's going to be all consonants. It's going to be all consonant letters. So hope that makes it clearer. So that is how we define the complementary sets and how we can represent it. What is the cardinality of a set? That is what we are going to be looking at now. Cardinality might look like a big English expression, but in this tutorial we are going to be looking at the meaning of cardinality of a set. And to put it, cardinality is as simple as saying the total number of elements in the set is referred to as the cardinality of a set. Let me put that again. The numbers of elements in a set is referred to as the cardinality of the set. For example, we have a set A which has the elements A, B, C, D and E. So can you guess what is the cardinality of this set? So how many elements do you have in this set? 1, 2, 3, 4 and 5. So the cardinality of this set is 5. Simple as that. The total number of elements in a set is referred to as the cardinality of a set. And conventionally, cardinality of a set is represented by this number of elements in set A. So I'm taking set A under consideration now. Number of elements in set A is referred to as the cardinality of the set. So if you are to put this from the previous example, you can say that n A, which is the cardinality of set A, equals to 5, and that is it. That is what it refers to as the cardinality of a set, the number of elements in the particular set. Now let's look at an example. Here we have some sets. We have the universal set which includes A, B, C, D, E, F, G and H. These are the letters. And we have set X which includes B, E and G, and set Y contains A, B, D and G. So the first one, we have to find N, U. So you have already seen that this symbol represents the cardinality of the set. So this is the cardinality of the universal set. So how do we find the answer to this? Number of elements in the universal set. Let's count 1, 2, 3, 4, 5, 6, 7 and 8. So we can say that the cardinality of the universal set is 8. That is, the number of elements in the universal set is 8. Now the second one, we have like a string of operation here. We have to find the number of elements in set Y plus the number of elements in complement of set X. Now to simplify this, let's firstly find the number of elements in set Y, and this is what? 1, 2, 3, 4. So this is 4. Now the second part, which is the number of elements in X prime. To make it easy, let's find what X prime is. Okay, I'm going to find X prime here. I have already looked at prime to means the elements in the universal set that are not in that particular set. So what do we have in universal set that are not in set X? We have A, B is in X, you have C, D, you have E in X, F, you have G in X, and H. So this is our X complement. So what is the number of elements in X complement? This is 1, 2, 3, 4, 5. So this is 5. Now going back to our question, which says number of elements in set Y, which is the cardinality of set Y, plus number of elements in X prime. Number of elements in set Y is 4, plus number of elements in X prime, which is 5. And the answer to this is 9. So that is the answer to the second part of the question. So that is simply how we define our cardinality of a set. Now I want you to try this. You can pause this tutorial now and feel free to post your answers in the comment section below. We have universal set, which is given to us as all the days in a week. We have set X, which is all the days in a week starting with the letter T, and set Y, which includes all the days in a week ending with the letter Y. So list the elements of set universal set. This is the element of set X, the element of Y, and find number of elements is X plus the number of elements in Y. So I would like to see your answers. One of the things you often come across in questions is the intersection of a set, and this can be defined simply as where two or more sets intersect. Okay, I'm still using the word intersect. It simply refers to as the common elements between two sets. It might be two or more sets. Given that we have two sets A and B, the intersection of A and B is a set which consists of the elements that are both in A and in B. Let me take that again. The intersection of A and B is a set which consists of all the elements that are both in A and B. For example, we have set A, which equals to A, B, C, D, and E, and we have set B, which equals to C, D, E, F, G, and H. So if you look at these two sets closely, we can see that there are some common elements between the two sets. We have C, D, and E. So these sets of C, D, and E simply refers to as the intersection. But before we continue, how do we represent intersection in sets? Intersection is represented with a letter that looks like N, but it's not N, just like something like this. Yes, something like this. So that is simply how we represent intersection. So we can see that the intersection of A and B, A intersection B, that's how this is being read. A intersection B. So A intersection B will now be equal to the sets of C, D, and E in this case. Let's clean this off and look at another example. So let's look at another set P and Q. So I'm cleaning this. So we are looking at another set P, which has the elements 2, 4, 6, 8, 10, 12, 14, and 16. These are even numbers. And we have set Q, which contains the elements 2, 4, 10, and 20. So to look for the intersection of these two sets, as I said before, where two sets, where they join together, what's the common element between those sets? So we can say P intersection Q is a set which consists of all the elements that are both in P and Q. We have 2 in P, we also have 2 in Q. We have 4 in P, we also have 4. We have 6 here, there's no 6 here. We have 8, there's no 8. We have 10 here, we also have 10. 12, 12, 14, there's no 14. 16, there's no 16. And we have 20 here, but there's no 20 in set P. So we have only 3 elements of sets which consist of 2, 4, and 10. And these are the elements of P intersection Q. So that is simply how we define the intersection of two sets. Simply remember that this symbol is used to represent intersection. The other category that often goes along with intersection is the union. And the union of a set is simply defined as the combination of the two sets. Given sets A and B, the union of A and B is a set which consists of elements that are either in A or B, or elements that are in both. Let me take that again. Given sets A and B, the union of A and B is a set which consists of elements that are either in A or B or both. For example, we have sets A to be equal to A, B, C, D, and E, just like we see in the previous example, and we have set B to be equal to C, D, E, F, and G. So to look for the union of the set, but before we proceed, let's look at the symbol to represent union. And this is quite easy to remember because union is just like U, and this stands for union, like U for union. So it's a letter, it's not exactly letter U, but it looks like U, just like this. So to write out the elements of A union B, which is A union B. So we are going to look for elements that are either in A or B or in both. We have A in A, B in A, and C in A. Even though all these elements are not in set B, we also include it as part of the union. We have C and C, yes, we put only one C. We have D and D, we put only one D. We have E in both sets, we put only one E. We have F in B, but not in A and G. And this is the union of these two sets, A and B. So this is simply the way and how we can represent the union of sets. If you have set A, let me use another example. We have set X, which consists of 1, 2, 3, and set Y, which consists of 1, 4, 3. You can write that X union Y equals to the set which consists of 1, 2, 3, and 4. So which number we can see in either A or B, in this case in either X or Y, is part of the union of that two sets. After talking about intersection and union, the next section that will be appropriate for us to move into is disjoint sets. Disjoint sets. Two sets A and B are said to be disjoint if there is no common element between them. That is, we have two sets A and B, and there is no common element between these sets. Recall from intersection that we refer to intersection as the common element between two sets, and the union of a set as the elements in both sets. Now, this set is talking about two sets in which there's no any common element between them. That is, A intersection B is an empty set, or we say it's an empty set. Let's take a look at an example. If you have set X, which equals to 1, 2, 3, 4, and set Y, which is a set of alphabets A, B, C, and D. If you have X intersection YA, which is the common element between X and Y, there's no any common elements we have, so we have an empty set here, or we write. So now that there's an empty set, we say that sets X and Y are disjoint. Set X and Y are disjoint. So that is that about disjoint sets, sets in which there's no any common element between them. In this section, we are going to be talking about power sets. The power set of a set A is a set of all the subsets that can be derived from set A. I take that again. The power set of set A is a set of all the subsets that can be derived from set A. At the beginning of this tutorial, we talked about supersets and subsets. So given a set A, which is a superset in this case, now all the subsets that can be derived from set A is referred to as the power set of set A. For example, if you have a set A to be equals to 1, 2, and 3, all possible subsets that can form from this superset is referred to as the power set of A. And before we proceed, one thing you have to notice that the empty set is part of the superset. So let's write out the superset of set A. But before we write that, Note that power set is denoted as power set of A. So this is the representation of power set of A. Now we have set A to be equal to 1, 2, and 3. Let's write out the power set. So the power set of set A will now be equal to, the first one is the empty set. That will be the first set we can derive from set A. And second, we take each of the elements 2, 3. Now we take each of the elements 1, 2, 3. So those are subsets that can derive from set A. We still have, we can take 1 and 2. We can take 1 and 3. Let me continue. Here we can take 2 and 3. And lastly, we can take 1, 2, and 3. So this is the power set of A, the set of all the subsets. So we have these subsets: empty sets 1, 2, 3, 1 and 2, 1 and 3, 2 and 3, 1, 2 and 3. So this is the power set of set A. The more elements we have in a set, the more it will be difficult to write out the power set. But to make it simpler and for you to track your progress, let's look at the formula. Note that power set of set A is referred to as, is denoted as P into brackets A. This is power set. And the cardinality of set A, which is the number of elements in set A, is denoted as this. So now if the number of elements in set A equals to m, then the number of elements in the power set of set A will be equal to 2 to the power of m. Now, for example, here we have set A, this set, and we have the number of elements in set A to be equal to 3. Now to get the number of elements we are going to have in our superset, we just take 2 to the power of 3 and we have 8. So if you count this, 1, 2, 3, 4, 5, 6, 7, and 8. So we have 8 elements in the power set of A. So this is how we can determine the number of elements that's going to be inside the power set of a particular set. Let's proceed. Here, let's check out an example. Here we have a question. It says set P equals to x such that 1 less than or equal to x less than or equal to 5, and set Q equals to x such that 2 less than or equal to x less than or equal to 8, where x is an integer, a subset of the universal set U equals to x such that 1 less than or equal to x less than or equal to 10. Use the following information to find the following. So the first one we have to look for P intersection Q, the second one P union Q, the third one P union Q complement, and the fourth one the number of elements in the power set of Q. So let's start from the first one. But before we do that, let's start at the elements of set P and Q. So definition has been given for set P here to be 1 less than or equal to x less than or equal to 5, and here we have where x is an integer. So we are starting from 1, since we have less than or equal to 2, 3, 4, and 5. And for set Q, we have 2, 4, 2, 3, 4, 5, 6, 7, and 8. So these are the elements of set P and set Q. So the first question is P intersection Q. Let's write the element of this set P intersection Q. P intersection Q means the common elements between P and Q, and then we have 2, 3, 4, and 5. 2, 3, 4, and 5. So this is the set P intersection Q. The second one, which is P union Q. So these are the elements that we have in P and Q. It can be in the 2 or be in 1, so you put everything together. So here we have 1, 2, 3 to 5, and here we have 2, 3, 4, 5, 6, and 7. If you check very well, we have all these as the common elements, and we have this as separate 1 and from here to here. So we just simply write out from 1, 2, 3, 4, 5, 6, 7, and 8. So this is P union Q. The third one, which is P union Q prime, the third one. So that is the complement of P union Q. We have already gotten the value for P union Q here. Now, in talking about complements, we said complements are those elements in the universal set that are not in set that we are considering. Here, to complete this, let's write that the elements of the universal set. This is 1 less than or equal to x less than or equal to 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these are the elements of the universal set. Now, we now look at elements that are in the universal set that are not in P union Q. We have 1 to 8 in P union Q, and then we have 1 to 10. So what we have here that are not in P union Q are 9 and 10. So these are the elements of P union Q prime. The third one, of the fourth one rather, we have number of elements in the power set of Q. In the last tutorial, in the last slide, we look at a formula for getting the number of elements in the power set. Now, the first thing we have to look at is the number of elements in set Q, which equals to 1, 2, 3, 4, 5, 6, 7. This is 7. So to get the number of elements in the power set of Q, we simply raise 2 to the power of 7. And this equals to 128. So we have the number of elements in the power set of Q to be equal to 128. So if you want to write out all the power sets of set Q, you are going to be having 128 elements. That might take a quite long time for it to finish. So, but you can still use this to track your progress, whether you have reached the last or not, since you already know that you are going to derive 128 sets. So let's continue. To round off this tutorial, let's do some introduction to Venn diagram. To learn more on Venn diagram, check out our tutorial on solving set equations using Venn diagram. Link in the description below. Venn diagram is simply a way we can represent sets using diagram. Historically, this method was developed by the man named John Venn. Let's write that, John Venn. So the diagram was named after the Venn diagram. So Venn diagram consists of a rectangular or a square shaped with inscribed circles. It can be in any format. This is 2. It can be in, my drawing is not perfect. Okay, so let's redraw this. This is simply a Venn diagram. So it consists of a circular or circles inscribed in a rectangularly shaped object. The operation union, intersection, complement of sets can easily be shown or visualized using Venn diagram. Let's look at how we can use Venn diagram to visualize the operation intersection, union, complement, and other set operations. Since this is just an introductory part to Venn diagram, let's quickly look at how you can represent a given set in a Venn diagram. Let's say, for example, if you have a set whereby the universal set is expressed as 1, 2, 3, 4, 5, and the set A is expressed as 2, 5, and 1. So how do you represent this using a Venn diagram? So we are going to draw a rectangularly shaped, and since we are considering only one set, whatever is inside this rectangle is part of the universal set. So we mark this rectangle as the universal set. And here, since we are considering only one set, we put a single circle inside the rectangle, and we mark this set A. So all the elements that we have here, we bring them into set A, which includes 5 and 1. And the elements that we have in universal sets that are not in set A, we just take them outside of the circle, and this includes 3 and 4. This can be placed anywhere the other does not matter, and the element does not matter. So that is simply how you can represent a given set using a Venn diagram. Let's look at some set operations represented using Venn diagram. So the first one we are going to be looking at is the intersection. So if you have a Venn diagram, we are going to explain this. Okay, we have two circles. So the circle represents the sets. So this is set A, and you can say this is set B. And the whole box covers our universal sets. In Venn diagram, all the elements inside a particular circle are the elements of the set that is being marked with that circle. So if you have the elements A, B, C, D, E, F, A, so C, D, E, F are the elements of B, and A, B, C are the elements of A. Now, to represent intersection, intersection is the point in which these two sets joined. So all elements that falls in this range falls to the intersection. So this is A intersection B. A intersection B. So the shaded part, as we said earlier, is the A intersection B. All elements that falls in that particular part of the circle are the intersection between set A and set B. Let's look at union. Okay, we have another Venn diagram, and again we have two sets, set A and set B. Since we say that union is the set that consists of all the elements in both A and B, so the union of this set covers all elements that falls in this range. So this is A union B. So all element that falls in this part of the circle, in this shaded part, belongs to A union B. Let's look at the third one, which is complement. Again, we have another rectangle and we have a circle. This is complement. Let's look at a single set A. We talk about complement as the elements that are inside the universal set but are not in set A. So since we already have all the elements of set A here, and assuming we have some elements here which is D, E, and F, these elements falls as part of the set but they are not in set A. So all elements that falls outside of the circle, so all the shaded parts refers to elements that are part of A complement. So this is A complement. All the areas after or outside the circle. So these are the basic representations using Venn diagram. We look at intersection, union, and complement. Let's take a look at an example. If you have to find A union B complement. So let's draw a Venn diagram for this. We're looking for A union B complement. So let's bring out our A and B. So this is A, set A, and this is set B. So this is the universal set. So since we have our A union B, as we have in this set, to be the set that covers both circle A and circle B, then complement are those elements that are not inside this horizontal line. So they are the element that falls in this range. So the vertical line represents A union B complement. So all elements that falls outside of the two circles is the complement of set A union B. So if you have some elements here, A, B, C, D, so outside the circle are the element that represents A union B complement. Let's clean it off to show it better. So we have used a shaded part to represent A union B complement. You can try it for others like A intersection B complement. You can try this. If you get it, feel free to post the challenge in the comment section below. Let's look at this example on Venn diagram. So we have a diagram here and we have to look for the answers to the following questions. The first one, say what are the elements of universal set U? So the elements of this universal set U consist of all elements inside the rectangle. So let's start from set M. We have K, E, F, K, E, F. In the intersection part, we have C and D. And moving to set N, we have G, I, and H. And outside the set, we have J, B, and A. So these are the elements of universal set U. So we have derived it from the Venn diagram. The second one is the element of M. So the elements of M includes all elements inside the set M, including the intersection part. So here we have K, E, F, C, and D. The third one, to write out the element of set N. And in set N we have G, H, I. We also have C and D. The fourth one is to write M intersection N. And we'll see this in the previous slide that the point whereby these two sets joined is intersection. So we have the element of M intersection N to be C and D. The fifth one is M complement. M complements are the elements that we have in the universal set but are not in set M. So we can see that the element we have in set M includes this. And to look for M complement, we are going to take every other thing apart from what we have in the circle M. So let's start from taking element that we have in N, which includes G, I, and H. We are not going to take C and D because C and D is also included in set M. And going outside of the two circles, we have J, B, and A. So these are the elements of M complement. The last one, which is the sixth one, is M union N complement. So these are the sets or elements that are in the universal set that are not in M union N. M union N, we have all this for M union N, as we saw in the previous slide. Let me clean this off. Okay. So these are the elements that covers for M union N. So what we have in the universal sets that are not in this range includes all things that we have outside of the two circles, and this includes J, B, and A. So this is simply M union N complement, and that is how we can solve questions from Venn diagram. This is just an introduction. You can check out our tutorial on solving set operations using Venn diagram to learn more, even about having three combinations of circle in Venn diagram. So try this to round up the tutorial. Try to look for M complement union N complement from the Venn diagram, and the second one, M intersection N complement using the Venn diagram. So that's it for this tutorial. As usual, to round off the tutorial, let's look at some applications of sets. Now we have been talking about sets, some basic computation using sets, the Venn diagram, and others such as the intersection, the union, the disjoints, and host of others. So how do you apply this in real life? How do you apply sets in real life? Sets are used in statistical computation, in measurements of population sizes, in segmentation, in a lot of ways in statistics. And the second, which I want to emphasize on, is the use of sets in business and marketing. Business is very useful in business. Sets is very useful in customer segmentation. How do you classify your customers? These are the customers that are looking for mobile phones. These are the customers that are looking for laptops. These are customers that are looking for this and that. So you can use sets in classifying your customers. It's used in business, as I said, and marketing. And that's it for this tutorial. Have a nice day.